Modern enterprise automation relies almost entirely on centralized cloud servers. The intelligence that runs factories, logistics networks, and corporate infrastructure lives in remote data centers, tethered to local machines by fragile fiber optic cables. This architecture introduces severe points of failure: a severed wide area network line, state-level censorship of internet traffic, or a localized outage at an AWS facility instantly severs the connection between the physical hardware and its digital brain. When that internet connection drops, highly advanced infrastructure instantly reverts to dumb metal. Robotic arms freeze, solar microgrids fail to balance loads, and automated security systems go blind. Even when the connection is stable, defense contractors and corporate architects face a severe constraint known as the privacy paradox. To remain competitive, these organizations require the cognitive power of large language models. A large language model, or LLM, is an AI algorithm trained on massive datasets to understand and generate human language and code. However, sending proprietary source code or classified schematics to public APIs violates operational security and legal compliance. This creates a strict engineering challenge, achieving enterprise-grade AI cognition and physical automation entirely offline. True infrastructural resilience requires severing the cloud tether entirely. The network must move from a collection of passive, connected devices to autonomous nodes capable of operating in a self-contained island mode. The foundation for this offline intelligence is the Sovereign Sentry Pro. This serves as the mandatory compute substrate for edge AI. Standard IoT gateways are designed to simply collect sensor data and forward it to the cloud. They lack the localized processing power to run dense cognitive algorithms on their own metal. The Sentry Pro utilizes a specific silicon architecture featuring an integrated neural processing unit, or NPU, a specialized chip designed specifically to accelerate machine learning tasks, paired with a unified memory structure. This hardware demands a strict minimum of 32 gigabytes of RAM. That exact memory footprint is required to hold a quantized 8 billion parameter Llama 3 model entirely in local memory. Quantization is a technique that compresses AI models so they can run on consumer-grade hardware without requiring massive server farms. Alongside the RAM, the node requires 4 terabytes of NVMe storage. NVMe stands for Non-Volatile Memory Express, a hardware protocol that allows data to be read and written at extremely high speeds. This massive high-speed storage is dedicated exclusively to housing local vector databases. These databases store mathematical representations of millions of pages of proprietary company knowledge, from legacy schematics to secure source code. Without this extreme physical density of compute and memory located at the edge, air-gapped autonomy is physically impossible. Sitting directly on top of this hardware substrate is Layer 2, the OpenClaw agent framework. This is the logic engine that executes a fully contained retrieval augmented generation, or RAG, pipeline. RAG allows an AI to search a private local database for factual answers before generating a response, ensuring accuracy without internet access. We can observe this operating in the Field Medic agent, deployed for remote heavy equipment maintenance in offline zones. A technician working in a cellular dead zone photographs an unidentified broken mechanical component on a legacy solar pump. The local vision language model processes the image. It performs a multimodal extraction, identifying visual features like bolt patterns and casting marks. The AI executes a semantic lookup against the NVMe vector database, cross-referencing the image against millions of pages of legacy service manuals in milliseconds. Using zero bandwidth, the agent identifies the part, synthesizes a step-by-step bypass guide, and highlights the exact bolts the technician needs to remove. For strict enterprise security, the same cognitive layer powers the DevOps Sovereign. A system architect pushes proprietary source code directly to a localized air-gapped Git repository hosted entirely on the Sentry node. The OpenClaw agent reads the code differences locally, analyzing the logic to spot security vulnerabilities or race conditions. This cognitive layer transforms a passive storage node into a localized reasoning engine. Intellectual property is analyzed, diagnosed, and repaired without a single packet of data leaking to external tech companies. Digital intelligence holds little value if it cannot interact with the physical world. Layer 3 provides physical actuation. The system translates software code into heavy machinery commands using node-read logic and direct general-purpose input-output, or GPIO, serial connections. GPIO pins allow microcontrollers to send and receive raw electrical signals to external hardware. The industrial Foreman agent utilizes this layer to manage off-grid energy. The AI continuously monitors the inputs of a solar microgrid, cross-referencing battery charge states against localized weather barometer forecasts. If the battery hits 95% capacity, the AI triggers physical RS-485 relays. An RS-485 relay is an industrial communication standard used to control heavy electrical equipment. The agent opens water valves or activates heating elements, storing the excess energy physically rather than wasting it. Some scenarios push beyond simple electrical relays.
A catastrophic server freeze can render Remote Secure Shell, or SSH, access completely useless. SSH is a cryptographic network protocol used to operate network services securely over an unsecured network. To address this, DeReticular developed the Sovereign Helping Hand, a 6-axis robotic manipulator. The OpenClaw agent strips away the proprietary cloud tethers of the hardware and runs an inverse kinematic solver locally. Inverse kinematics is the mathematical process of calculating the exact joint angles needed to position a robotic arm at a specific target. When a remote server locks up and digital access fails, the robotic arm physically reaches out and depresses the hardware reset button on the chassis. This layer gives the AI a physical body, granting remote infrastructure the capability to self-regulate, self-balance, and physically self-repair without human intervention. If an autonomous system takes a physical action completely offline in a remote factory, external auditors face the Oracle problem. They need a way to mathematically verify that the event actually occurred as reported. Traditional operations rely on centralized databases and human oversight, both of which can be altered or corrupted. A dedicated microcontroller designed to secure hardware through integrated cryptographic keys. The node uses this chip to cryptographically sign its local sensor telemetry and AI decisions. The Aerospace Forge applies this trust layer to remote contested logistics and 3D printing. During a 40-hour offline 3D metal print, the local AI uses multimodal vision to monitor the thermal temperatures of the laser melt pool, checking for microscopic warping layer by layer. Once the print finishes, the AI hashes the entire 40-hour telemetry log and commits the mathematical signature to the distributed ledger. This generates a digitally verifiable FAA Form 8130-3, an airworthiness approval tag that allows a remote inspector in another country to instantly verify and approve the manufactured part. This final trust layer replaces the need for physical human proximity and vulnerable third-party auditors with immutable mathematical proof of action. When this 4-layer architecture scales outward, individual sovereign nodes form a highly resilient macro-level economic network. The exact same hardware and software stack applies across entirely different industries. The agronomist balances crop yields, the dockmaster secures marina billing, and vault warden protects physical art. These independent units network together into an interconnected peer-to-peer mesh that routes communication and settlement data around traditional telecom outages. Enterprises transition away from paying continuous vulnerable software subscriptions to tech monopolies and instead own their localized, perpetual AI assets outright. By distributing the intelligence directly to the edge, the architecture eliminates the centralized cloud databases that serve as massive targets for data breaches. Infrastructure stops waiting on delayed human reaction times to fix problems. It executes proactive, zero-latency machine intelligence at the precise moment a sensor detects a failure. True infrastructure resilience requires animating the edge. Sovereignty means the system possesses the capability to think, act, and verify itself entirely on its own metal.